Well, hello everyone, welcome back to Coding with Lying. This time we're in episode 3, and what you see before you in this very roughly, quickly put together kind of demonstration of Java code, yada yada, thing is more or less what we decided on last time. So we've got calculations for each layer and calculations for each neuron, and we are going to be looping through them all to actually get the full calculations of what every neuron is saying, to then figure out eventually what the neurons are coming to. So let's see, stored in inputs. There, comment. Now, what we need to decide today is how we are going to actually store the data for each individual neuron. Because every single individual neuron is going to need a reference to an input value, see input ID here, a weight value, and potentially, this is one of the big discussion topics for the day, designation of its activation function, because there's 3 main different activation functions, linear step, non-linear step, and sigmoid. Just very briefly, those are the 3 main ones. And then we also need to talk a little bit about how we are going to store this data with regards to individual entities. Because since the idea is that eventually, a little bit later down the line, all of these entities are going to actually be having their own different individual network values, so that they'll react differently to a given environment. So we can't just hard code them in. We can't just hard code the network data in here, say somewhere up here. So hard coded neuron data there, and then we just have this whole thing reference that. Because that will make it impossible for the individual mobs to actually understand that. It'll just all be, here's a task, here's the way that it handles the data, go. So instead, and here, well, let me explain a little bit on this. If we do hard code the neuron data, it's going to be much more processor efficient, because we won't have to reference data through the entity, we won't have to pull stuff out, and theoretically we won't even have to break it into usable chunks. That's the next thing I need to talk about. But we'll have basically 0 versatility. Every single mob that uses this specific task will have the exact same neuron data and will react in exactly the same way. We'll effectively be back at square one. So we need to actually just wire it into the different entities. Now, next question. How? Because we need 3 values for every single neuron, and we need to also divide them by layer so that they're referencing at the right point in time, so that they're referencing the right version of inputs. Because remember, this gets overridden every time this runs around, so every layer is using the values of the neurons created from the previous layer, whether that be the initial inputs or not. The way I could do it is to potentially have an object. Java is an object-oriented language, so I could create a neuron class, which has activation function and weight value, input value, that kind of stuff, and then just make an array of that. But it would be very big on memory, and would not be good, considering that I'm trying to pay a lot of attention to how efficient this whole system is being, because whilst all of these decisions are fairly small right now, which is why you might be curious as to why I'm spending so much time on them, they add up extremely quickly. So if we have, say, just one of these tasks, where the network is only, say, a dozen different neurons, arranged however we need them to be, then these calculations all need to be run for 12 different neurons. And then they need to be run every single time a single entity is checking for this task. And then they need to be run that same number for every single member of the same population. So every single entity of that type that's using this same task. So it's 12 times the activation rate, effectively, times the population size of the entity that actually has this task. So it scales up very quickly. So as a consequence, I need to make this as efficient, or I'm going to basically murder frame rates. That's the long and short of it. If I'm not careful, I will murder someone's frame rate with this. So, the method that I've come up with for storing the data inside of the... We'll store it hard-coded in here for the time being, and we'll switch it over to being individual entities later. The method that I've come up with is to have a string. So let's call that end-data, string end-data. And then, within that string, we're going to have things subdivided by what layer they are in. So let's say we have that, and the different the different layers are broken apart by a key character. So, for example, let us use that. So that defines first, second, third, and fourth layers. Now, whenever we want to actually get to individual layers, just ahead of this, we can do end-data.split by that. So, to get the different strings, we just use strings layers equals end-data.split by that. There. So what that does is it takes our string, so say ASDF, it takes our string end-data, and it splits it into an array of strings, which I should highlight that, wherever that happens. Now we can also limit it to however many we want, so if we only wanted 3, we'd have the number 3 after that, because split has a couple different versions of itself. But this is the main important part. So every time that we need to subdivide this into a new sort of category, we just run this same thing with the right character that we're looking for. So from there, we can reference the layer data here by referencing a specific entry in strings. So if we get string layer data equals string equals layers L, that gets us the data for this specific layer. Then we have to break it apart to get the individual neurons. So we need another subdivider. So let's say we have A, B, C in the first layer there. So to reference that, we're going to use this second character, this curly right bracket, and split the layer data here apart by it. So string neurons, or string neurons equals layer data dot split curly right bracket. And that gets us all of the neurons on this layer. In fact, we can just reduce this a little bit by doing that. So that gets us all of these neurons. And then we now need to split those apart into their individual inputs and weights, and we have to finally address the matter of the activation function, because as I said, there's a few different ones, and they have different benefits and disadvantages. So for example, linear step is basically a greater than operation. So if this value is greater than this value, then it outputs true, if not false. It reduces things to binary, and it's very good if you're only ever doing binary stuff. We are not, however. In fact, most of our numbers are going to be fairly large, sort of real-world float numbers, like distance to a target, for example, in the case of fleeing, or hunger level, in the case of where it should eat some food. So we need to take into account that we're going to have very non-binary numbers, which means linear step, whilst it may be useful for points after the first step inside of the arrays, inside the networks, so past the input array when things are initially scaled down, it's not very good for functioning the entire network. Linear step is a little bit better because it's sort of it's a sine curve basically. So it's up and down, and there's a middle point that we are calling true, and everything else is more or less false. That's also handy because it means that we can have them flee within a certain range and ignore it otherwise. But again, we have issues because our data isn't uniform. It's not all the same kind of data. So the ID number, for example, of whatever mob you're checking whether you should flee from, if it turns out it's a sheep, then that's not a range, that's not binary, it's something else. Sigmoid is probably the one that we're going to limit it to. I think Sigmoid, it's kind of a tricky one to explain, but Sigmoid, when used in neural networks, is essentially mimicking how different things act upon human neurons. So it's the most accurate in terms of doing this. There's a few different things you can try to improve the accuracy on the other ones, but for now we're just going to focus on this one. It's a mathematical function, fortunately, which Java also has a built-in function, so I could cheat and just not make my own. I might try it later on. We'll see if I have extra time. But if we were to have activation function as a function of as something that individual neurons can work out, then we have the problem that we need a split point to determine which activation function it is. So linear step, nonlinear step, Sigmoid function. And then we also have to have things like the maximum number for things like linear step, the minimum number for linear step and stuff. So we have to have the activation function and all of its required variables. So if we have activation function, we have to do a lot more calculations. So ultimately, I think we're just going to stick with Sigmoid, and we'll see exactly how that impacts the network later. I think it'll be okay at this point in time. But ultimately we'll find out. My main concern right now is getting this operational, and hopefully not crippling anything. So we need a split point to get our list of these input values and weight values, which will be stored as pairs inside of the neuron data. So we need to retrieve our information on this specific neuron. So for that, we need string, let's call it binds, equals neurons n dot split, and let's have our split variable be greater than, since we just mentioned it anyways. So that will give us our list of input value, weight value, and then we can just run a different thing on. We can just use it inside of here to get what we need. We are going to want a we'll get strings for now. I won't go into the absolute nitty-gritty here because this is just an example thing. So string binding equals binds w, and then we can split that apart to get the input ID, which references the preceding array, the inputs, and multiply that by the weight, which we can also get from the same thing. And then we use our activation function on that, Sigmoid, and we put that, and once that's calculated everything, we shove that through into the temp array to replace the inputs for the next level. So that is it for today. I really hope I've explained things a little bit better. If you remember the little graphic from the previous episode that showed you how neurons function, that's more or less what's happening in here. Give or take, and this is where it actually gets into the arrays that we discussed. But with all of that, I should call it a day, and I shall catch you next week when we are most likely going to be talking about how these neurons are going to work out as well. So with that in mind, I shall catch you all next time.